3I Atlas traveled 60 kilometers per second toward our sun, and every physicist watching expected the same outcome: fragmentation, disintegration, death. Small icy bodies don't survive perihelion passage. The math is brutal, the precedent clear. Except 3I Atlas refused to follow the script. It approached, endured forces that should have ripped it apart, and emerged intact on the other side. Scientists checked their instruments twice. The data didn't change. Now, we're confronting an uncomfortable possibility. Stay until the end, because the mystery deepens with every telescope that studies it. 3I Atlas survived when it shouldn't have. Picture this. January 13th, 2025. An icy visitor from beyond our solar system, traveling at 60 kilometers per second, plunges toward the sun. Scientists around the world watch their screens, waiting. They've seen this story before. They know how it ends. Small bodies approaching our star at perihelion, their closest point, usually shatter like glass under a hammer. The heat is unforgiving. The tidal force is brutal. Volatile ices boil away, creating internal pressures that rip these objects apart from the inside. It's not a question of if they'll break, it's a question of when. But 3I Atlas doesn't break. It survives. And nobody can explain why. Now, before we go further, let's establish what we're talking about when we say perihelion. It's the moment when any orbiting object reaches its closest approach to the sun. For comets especially, this is the danger zone. Solar radiation heats the surface to extreme temperatures. Frozen gases sublimate directly from solid to gas, creating jets that shoot material into space. These jets can spin the object faster, creating centrifugal forces. Meanwhile, the sun's gravity creates tidal stresses, trying to pull the near side more strongly than the far side. For a loosely bound object, what we call a rubble pile, this combination is usually fatal. We've watched countless comets die this way. They brighten as they approach, then suddenly fragment into pieces. Sometimes they vanish entirely, reduced to clouds of dust. The sun is a furnace and a crusher combined. Small icy bodies, especially those from the outer reaches of stellar systems, simply aren't built to survive prolonged exposure. 3I Atlas should have been no different. In fact, it should have been more vulnerable. This object didn't form in our solar system. Its trajectory is hyperbolic, meaning it came from interstellar space, possibly traveling for millions or billions of years before encountering our sun. Objects that spend eons in the deep freeze of interstellar space should be pristine, ancient, fragile. They're time capsules from other star systems, but time capsules made of ice and dust, not titanium. Yet here's the puzzle that keeps astronomers up at night. 3I Atlas approached the sun and remained intact. No major fragmentation events. No sudden disintegration. The telescopes watched it swing around perihelion at approximately 1.4 astronomical units, about 210 million kilometers from the sun, and it just kept going. Whole, coherent, defiant. Think of it this way. Imagine taking a snowball and throwing it past a massive industrial furnace at highway speeds. You'd expect it to melt, to break apart, to spray water vapor everywhere. Now imagine it emerges on the other side, essentially unchanged. You'd start asking serious questions about what that snowball was really made of. Was it actually ice? Was there something inside protecting it? Did someone engineer it to survive? That's where we are with 3I Atlas. The stakes here go beyond one weird object. Because 3I Atlas is interstellar, it represents a sample from beyond our solar system. Everything we learn, or fail to learn, from it shapes our understanding of how planetary systems form elsewhere, what kinds of materials exist in the galaxy, and what we should expect when the next interstellar visitor arrives. And they will arrive. We're getting better at detecting them. In 2017, we spotted one I/Oumuamua, the first confirmed interstellar object. In 2019 came two I/Borisov, now 3I Atlas. Each one has been strange in its own way, but this one might be the strangest yet. Scientists expected 3I Atlas to behave like a typical comet, maybe with some exotic composition from its alien origin. What they got instead was an object that seems to play by different rules. The observations coming in from multiple telescopes and observatories don't fit comfortably into our existing models. The composition is bizarre. The way light scatters off its surface is unprecedented. Its structural integrity under stress seems impossibly high. What if this isn't just an unusual comet? What if 3I Atlas represents something we haven't seen before, a new class of object entirely? Or what if it's something we never imagined we'd find? The possibility space is vast and unsettling. When your models predict destruction and you observe survival, one of two things is true. Either your models are incomplete, or the thing you're observing isn't what you thought it was. You're watching this because you understand that space isn't just pretty pictures and interesting facts. You know that every anomaly in astronomy is a crack in our understanding, and sometimes those cracks lead to complete revolutions in how we see the universe. 3I Atlas is one of those cracks. A small object, yes, probably less than a few kilometers across. But its behavior has implications that ripple outward through planetary science, astrochemistry, and our understanding of what's possible in the cosmos. In the sections ahead, we're going to examine what the most powerful telescopes on Earth and in space actually observed when they studied 3I Atlas. We'll look at the chemical composition of its atmosphere, its coma, and why those chemicals tell a story that doesn't match anything we've seen before. We'll explore the weird way light bounces off its surface, measurements that have never been recorded for any other known object, and we'll confront the central mystery head-on. Given everything we know about physics, thermal stress, and comet structure, 3I Atlas should be a cloud of debris by now. But it's not. So ask yourself this question as we continue. When something survives what should destroy it, what does that tell us about the thing? Or about what we thought we knew about destruction? The James Webb Space Telescope turned its infrared eye on 3I Atlas and found something nobody expected. Using its near-infrared spectrograph, scientists captured detailed spectra of the object's coma, the cloud of gas and dust surrounding its nucleus. What they found was an atmosphere dominated by carbon dioxide. Not just containing carbon dioxide, dominated by it. The carbon dioxide to water mixing ratio came in at approximately 8.0, plus or minus 1.0. Let me put that in context. Your typical solar system comet has a very different recipe. Water ice is usually the star of the show, with carbon dioxide playing a supporting role. But 3I Atlas flips that script completely. For every one water molecule in its coma, there are roughly 8 carbon dioxide molecules. This isn't just unusual. This is chemistry that suggests either a radically different formation environment or some process that fundamentally altered the object's composition over time. Think about what this means. Formation temperature matters enormously for what ices condense out of a protoplanetary disk. Water freezes at higher temperatures than carbon dioxide. If you're building a comet in the inner regions of a disk, you get water-rich objects. If you're farther out where it's colder, carbon dioxide becomes more prominent. But to get a ratio this extreme, 3I Atlas either formed in an unusually cold region of its birth system, or something happened to it during its interstellar journey. The Webb telescope also detected other molecules in the coma. Water is present, despite being the minority volatile. Carbon monoxide showed up in the observations. Carbonyl sulfide, a more exotic molecule, appeared in the spectra, and perhaps most intriguingly, the instrument detected water ice grains, actual solid particles of ice floating in the coma. These pieces of evidence paint a picture of an active object, one that's shedding material as solar heating drives sublimation, but the proportions remain baffling. Now let's talk about polarimetry, because this is where things get genuinely unprecedented. Polarimetry measures how light waves align after bouncing off an object. When sunlight hits the dust and gas around 3I Atlas, some of that light gets scattered toward Earth. Depending on the properties of the material, grain size, composition, surface texture, the scattered light becomes partially polarized. By measuring this polarization at different angles, scientists can infer details about what they're looking at. A recent study reported something that made researchers check their instruments multiple times. 3I Atlas exhibited what's called an extreme negative polarization branch of approximately negative 2.7% at roughly 7-degree phase angle. The phase angle is just the angle between the Sun, the object, and Earth. What matters here is the behavior. Most objects show positive polarization at small phase angles. 3I Atlas showed strong negative polarization. Then, at around 17 degrees phase angle, the polarization inverted, switched from negative to positive. This behavior has never been recorded for any known comet or asteroid. Never. The closest analogs might be certain very red objects in the outer solar system, but even those don't match perfectly. The polarization signature suggests something about the surface or coma particles that doesn't fit our catalog of known materials or structures. Scientists are still working through what combination of grain properties, surface roughness, or composition could produce this signal. Right now, there's no consensus answer. Meanwhile, light curve data, measurements of how the object's brightness changes over time, revealed another puzzle. 3I Atlas did not show the dramatic fluctuations you'd expect from a tumbling, fragmenting body. Its brightness varied, yes, as you'd expect from rotation and changing viewing geometry, but the variations were relatively modest and regular. This suggests structural coherence. The object is rotating in a controlled manner, not wobbling chaotically like something that's breaking apart or has an irregular, unstable shape. Ground-based observatories captured images of 3I Atlas that showed distinct tail structures. The most prominent feature was a sharp ion tail, created when solar wind blows ionized gas away from the coma in the anti-solar direction. These tails are common for active comets, but observers also noted a faint anti-tail, a structure that appears to point toward the Sun. Anti-tails aren't mysterious. They're usually dust grains aligned along the object's orbital plane that create an optical illusion. But the presence and characteristics of these structures give information about dust production and particle size distribution. Then, there's the color and brightness behavior near perihelion. Multiple sources reported that 3I Atlas exhibited what's described as blue brightening. Most comets redden as you observe them, especially when dust dominates the coma. A blue trend suggests different scattering properties or a different mix of materials. Additionally, the object brightened faster than typical cometary models predicted as it approached the Sun. This rapid brightening could mean more surface area is active than expected, or the composition is sublimating more efficiently than standard water ice models suggest. Some preliminary reports mentioned sun-facing jets. Now, this requires caution because jet observations are complex and can be misinterpreted. Normally, jets on comets point away from regions heated by the Sun. The subsolar point gets hot, ice sublimates, and gas jets out. But if 3I Atlas has jets pointing toward the Sun, that implies something strange about its rotation state, surface properties, or thermal lag. Material heated on one rotation might outgas during the next, creating jets that appear misaligned with current solar direction. Or, more exotically, there could be some internal structure that channels gas in unexpected ways. Putting all these observations together creates a composite picture of an object that is genuinely anomalous. Extreme carbon dioxide dominance. Unprecedented polarization signatures. Structural integrity despite approaching perihelion. Unusual color evolution. Potential jet misalignment. Every single data point, taken alone, might be explainable with some creative modeling. But together, they form a pattern that doesn't match any template in our comet catalog. You're starting to see why 3I Atlas has the scientific community buzzing. This isn't a case of one weird measurement that might be instrumental error. This is multiple independent observations from different telescopes using different techniques, all pointing to the same conclusion. This object is not behaving like our models say it should, which means either the models are missing something fundamental, or 3I Atlas is something our models never anticipated. So the question becomes unavoidable. With all these anomalies stacking up, with this object proving it can survive conditions that should fragment it, with a composition and behavior profile unlike anything cataloged, what exactly are we looking at? And more pressingly, given that it should have broken apart by now, based on our understanding of comet physics, why didn't it? Let's talk about what kills comets. When a small icy body approaches the Sun, it faces a gauntlet of destructive forces that would make a medieval torture chamber look gentle. First, There's thermal stress. Solar radiation doesn't just warm the surface, it creates extreme temperature gradients. The side facing the sun might reach hundreds of degrees Kelvin, while the shaded side remains far colder. Materials expand when heated and contract when cooled. When this happens unevenly across a body, internal stresses build up. Crack formation accelerates. Structural integrity degrades. Then there's sublimation. Unlike melting, where a solid becomes liquid, sublimation jumps straight from solid to gas. When frozen volatiles like water, carbon monoxide, or carbon dioxide absorb enough energy, they transition directly to vapor. This process creates pressure. If gas is being produced faster than it can escape through surface pores or cracks, pressure builds. Inside the object, think of it as countless tiny explosions happening beneath the surface. Eventually, something has to give. The gas that does escape creates jets. Those jets produce thrust. Action and reaction. Newton's third law doesn't take breaks. When gas shoots out of one side of the object gets pushed in the opposite direction. These non-gravitational accelerations can be measured from Earth by tracking how the object's orbit deviates from purely gravitational predictions. But there's a darker side to jets. If they're not distributed symmetrically, they create torque. The object starts spinning faster. Centrifugal forces grow. For a loosely bound rubble pile, which many comets are thought to be, this increased rotation can overcome the already weak gravity holding the pieces together. Don't forget tidal forces. The sun's gravity decreases with distance. If you're a kilometer-sized object passing reasonably close to the sun, the near side experiences noticeably stronger gravitational pull than the far side. This differential force tries to stretch the object along the line, connecting it to the sun. For bodies with low tensile strength, this stretching can be catastrophic. We've seen comets pulled apart by tidal stress, transformed from single objects into chains of fragments. 3I Atlas reached perihelion at approximately 1.4 astronomical units from the sun. That's about 210 million kilometers. This isn't a sun-grazing pass like some comets that get within a few solar radii, but it's still close enough for all these destructive mechanisms to operate. The solar flux at that distance is substantial. Temperatures rise. Volatiles sublimate. Forces accumulate. Now consider the size problem. Determining the exact dimensions of 3I Atlas has proven difficult because we're observing reflected sunlight from a small, distant object surrounded by a coma that scatters and emits its own light. Different observation methods and assumptions yield different estimates. Some imaging analyses suggest a nucleus diameter of perhaps 320 meters. Others, using different techniques or modeling assumptions, arrive at figures closer to 5 or even 5.6 kilometers. This uncertainty matters enormously. If 3I Atlas is on the smaller end of those estimates, a few hundred meters across, then it's even more vulnerable to disruption. Small bodies have less self-gravity holding them together. They have higher surface area to volume ratios, meaning more surface exposed to solar heating per unit mass. The forces trying to tear them apart have an easier time. But here's where the paradox deepens. Observations of 3I Atlas's activity, its jets, its coma production, the amount of gas being released, suggest a substantially active surface area. If you do the calculations assuming typical comet behavior, the amount of outgassing observed requires either a large nucleus with lots of active surface or a small nucleus where basically the entire surface is outgassing. The first scenario conflicts with some of the size estimates. The second scenario is unusual and raises questions about how such an object could maintain structural integrity while its entire surface is venting gas. There's another clue in the object's trajectory. When comets outgas significantly, those jets show up as non-gravitational accelerations, deviations from the orbit you'd predict using gravity alone. Careful tracking of 3I Atlas's position over time allows astronomers to measure these deviations. Preliminary analyses suggested that the non-gravitational acceleration was smaller than you'd expect, given the observed activity level. Some researchers interpreted this to mean the object must be more massive than the smaller size estimates suggest, implying a diameter exceeding 5 kilometers. But here's the contradiction. If 3I Atlas is that large and that massive, Where's all that mass hiding? Why don't direct imaging attempts resolve a bigger nucleus? Is the nucleus just very dark, reflecting very little light, making it hard to see against the bright coma? Or is there some disconnect between the mass inferred from orbital dynamics and the size inferred from imaging? Let's talk about what holds comets together. Many researchers think comets are rubble piles, collections of ice, dust, and rock loosely bound by weak gravity, and maybe some frozen together contact points. These structures are inherently fragile. Shake them too hard, and they come apart. Heat them unevenly, and thermal stresses fracture them. Spin them too fast, and they fling pieces off into space. For 3I Atlas to survive perihelion intact, it needs to be different. Maybe it has substantial tensile strength, meaning the material itself is strong enough to resist the forces trying to pull it apart. Maybe there's a solid core, or a reinforcing structure we're not accounting for. Maybe the interior is layered in some way that distributes stress more effectively than a uniform rubble pile would. Or maybe, and this is the speculation that keeps scientists up at night, 3I Atlas is built in a way we haven't seen before. What if interstellar objects, because of their unique formation or their long exposure to cosmic conditions, develop properties that make them more resilient than their solar system cousins? What if something about this object's journey through space fundamentally changed its structure? Think about what we're implying here. We have models for comet behavior. Those models aren't perfect, but they work reasonably well for the hundreds of comets we've studied from our solar system. 3I Atlas breaks those models. It survives when it shouldn't. It behaves in ways that don't match predictions. The simplest explanation would be that it's stronger than expected. But why is it stronger? What makes it different? The alternative is uncomfortable, but necessary too. Consider, what if our entire understanding of small body structure and behavior is based on a sample set, solar system comets, that isn't representative of the broader population? What if interstellar space does things to these objects that we haven't accounted for? What if 3I Atlas isn't an exception, but a preview of what we should expect when we get better at detecting interstellar visitors? Every anomaly in science is a doorway. It's an invitation to look deeper, to question assumptions, to expand the boundaries of what we think is possible. 3I Atlas is standing in that doorway right now, and it's not moving. So the question we have to ask isn't just why this one object survived. The question is what that survival tells us about the limits of our knowledge and the possibilities we haven't imagined yet. Scientists confronted with 3I Atlas's survival and strange properties have begun generating hypotheses. None have been proven yet. What we're about to explore exists in that productive space between speculation and theory. Ideas supported by some evidence, but requiring much more data to confirm or rule out. Think of these as the best guesses educated minds can make when the universe hands them something genuinely new. The first hypothesis involves cosmic rays, and it's gaining traction among researchers who study interstellar objects. Here's the core idea. 3I Atlas didn't form yesterday. It's been traveling through the galaxy for an unknown period, possibly millions or even billions of years. During that time, it's been continuously bombarded by galactic cosmic rays. These are high-energy particles, mostly protons, that cruise through interstellar space at near light speed. When they impact ices and organic materials, they trigger chemical reactions. Carbon monoxide can be converted to carbon dioxide. Simple organics can be transformed into more complex, refractory compounds. The surface layers get processed, altered, hardened. Over enough time, this bombardment could create a crust, an irradiated shell that's fundamentally different from the pristine interior. This crust might be mechanically stronger, more resistant to thermal stress, less prone to sublimation. It could act like armor, protecting the more volatile interior from rapid destruction when the object finally encounters a star. This hypothesis elegantly explains several observations. The extreme carbon dioxide dominance in 3I Atlas's coma could reflect this cosmic ray processing. Carbon monoxide converted to carbon dioxide over eons would naturally create a carbon dioxide-rich surface layer. When that layer heats up and sublimates, You'd observe the processed chemistry, not necessarily the pristine formation chemistry. The structural integrity, the survival itself, makes sense if the object has a tough outer shell that can resist fragmentation better than a typical comet. The model even offers an explanation for the unusual jet behavior. If the crust is thick and unevenly distributed, or if it has weak points where the interior is exposed, you might get jets emerging from unexpected locations. Perhaps the subsolar point is well armored, but a region slightly offset from it has a thinner crust. Gas builds up, finds the weak point, and vents at an angle that appears to be sun-facing when observed from Earth. But this hypothesis has question marks. How thick would this crust need to be? How long does cosmic ray processing take to create a shell strong enough to matter? We don't have laboratory experiments or detailed models for what billions of years of cosmic ray bombardment does to a kilometer-scale icy body. We're extrapolating from smaller-scale experiments and making educated guesses. The idea is plausible and attractive, but it's not proven. The second category of hypotheses focuses on exotic composition and structure. What if 3I Atlas contains materials we don't normally find in comets? Refractory minerals are substances that remain solid at high temperatures. If the object incorporated a significant fraction of these during formation, it would be more thermally stable. Sintered materials, particles that have fused together through heating or pressure, could create a stronger matrix than loose dust and ice. Some researchers have speculated about a layered structure. Imagine a hardened outer shell, possibly from cosmic ray processing, possibly from primordial formation conditions, with volatile rich pockets underneath. When solar heating penetrates through cracks or thin spots in the shell, those volatiles sublimate and escape, creating observed activity. But the shell itself holds the overall structure together, preventing catastrophic breakup. This model could explain the mismatch between observed activity and inferred nucleus size. If only certain regions are actively outgassing, maybe 10 or 20% of the surface, you can have vigorous coma production without requiring the entire nucleus to be sublimating. The rest is locked beneath that protective layer. There's even speculation about metal content. Could 3I Atlas have formed in an unusually metal-rich protoplanetary disk? Metals and silicates have much higher tensile strength than ices. A body with a significant rocky or metallic component would naturally be more resilient. The challenge with this idea is reconciling it with the observed volatility. You need enough ice to produce the coma and jets, but enough strength to survive. Finding that balance requires a very specific structure. Now we enter more speculative territory. There's a hypothesis that refuses to die, despite mainstream scientific skepticism. Some people, including a few credentialed astronomers, have suggested that 3I Atlas might not be entirely natural. The idea is that its unusual properties, the survival, the stability, the directed jets, the strange composition, could indicate artificial modification or even fully engineered. Construction. Avi Loeb, a Harvard astronomer, has been vocal about considering these possibilities, particularly after one I/Oumuamua exhibited its own suite of anomalies. The argument goes something like this. If an advanced civilization wanted to send a probe or vessel through interstellar space, they'd need to build it to survive the journey. That means resistance to cosmic rays, structural integrity under stress, perhaps even active components that could adjust trajectory or behavior. Some of 3I Atlas's properties might fit that profile. Let me be clear. This is not the mainstream scientific interpretation. Most researchers believe natural explanations are overwhelmingly more likely. The burden of proof for extraordinary claims is high, and right now, there's no direct evidence of artificiality. No radio signals that can't be explained by natural processes. No geometric patterns or structures in the imaging. No behaviors that absolutely require intelligent design. But the idea persists because it touches something fundamental in the human psyche. We're searching for life and intelligence elsewhere in the universe. When we encounter something we can't explain, our minds leap to possibilities. Could this be a sign we're not alone? The honest answer is probably not. But probably isn't certainly, and that gap is where speculation lives. The final set of hypotheses concerns formation environment. Perhaps 3I Atlas formed in a protoplanetary disk, very different from our solar nebula. Different stellar masses, different metallicities, different temperatures and pressures all affect what materials condense and where. A disk around a low metallicity star might produce objects with unusual compositions. A disk disrupted by a nearby stellar encounter might scatter, forming planetesimals into strange orbits, giving them unusual properties. The polarimetric data, that weird negative polarization signature, has led some researchers to suggest 3I Atlas might resemble trans-Neptunian objects or centaurs from the outer solar system, but from another star system. These cold, distant bodies often have red colors and unusual surface properties, from eons of exposure to cosmic radiation and maybe cryogenic chemistry. If 3I Atlas is an interstellar equivalent, we'd expect some unfamiliar properties. Each of these hypotheses explains some features while leaving others unresolved. The cosmic ray processing model handles the carbon dioxide and survival, but doesn't fully explain the polarimetry. The exotic composition ideas work for structural integrity, but require specific formation scenarios we can't confirm. The artificial hypothesis generates headlines, but lacks supporting evidence. The formation environment angle makes sense, but is frustratingly hard to test without more data. What scientists need now is more observations, higher resolution imaging to pin down the nucleus size, detailed spectroscopy to map composition across the coma and look for gradients that might indicate layering, polarimetry at more phase angles to constrain the scattering properties, long-term monitoring to track how activity evolves as the object moves away from the sun. 3I Atlas is moving away from us now. Every day it gets farther, fainter, harder to observe. We have a limited window to gather the data that might resolve these questions. The universe has handed us a puzzle with missing pieces, and we're racing against orbital mechanics and geometry to fill in those gaps before the opportunity closes. 3I Atlas has become more than a scientific curiosity. It's become a cultural phenomenon, a Rorschach test for how we interpret ambiguous data and handle uncertainty. The debates surrounding this object reveal not just disagreements about astrophysics, but deeper tensions about epistemology, public communication, and what kinds of hypotheses deserve serious consideration. The most visible controversy centers on the artificial origin hypothesis. On one side, you have the vast majority of the astronomical community arguing that invoking alien technology to explain natural phenomena is premature at best and scientifically irresponsible at worst. Their position is straightforward. We've studied thousands of comets and asteroids. We've seen all kinds of unusual behavior that initially seemed mysterious, but eventually yielded to natural explanations. 3I Atlas is strange, yes, but strange within the spectrum of plausibly natural variation. These scientists point to historical precedents. When pulsars were first discovered, their regular radio pulses were so precise that researchers half-jokingly called them LGM for little green men. But the natural explanation, rapidly rotating neutron stars, turned out to be correct. When fast radio bursts emerged as a phenomenon, some speculated about artificial origins. Natural magnetar processes seem more likely now. The pattern is clear. Anomalies usually have natural explanations once we understand the underlying physics better. On the other side, a smaller but vocal group argues that dismissing artificial origins out of hand is itself unscientific. They contend that the search for extraterrestrial intelligence is a legitimate scientific pursuit, and that means taking seriously the possibility that we might detect technosignatures, signs of technology, in unexpected places. If we automatically rule out artificial explanations before examining them, we risk missing something monumental. This debate gets amplified by media coverage. Headlines screaming about alien probes or mysterious interstellar visitors generate clicks and views. Public figures commenting on social media add fuel. Mainstream outlets, some responsible and some less so, pick up the story. Suddenly, 3I Atlas isn't just an interesting comet. It's a cultural touchpoint for humanity's loneliness and our hunger for cosmic companionship. Scientists have pushed back against the most sensational claims. When some reports suggested 3I Atlas might be emitting unusual radio signals, researchers examined the data carefully. The signals turned out to be consistent with hydroxyl emission, OH radicals produced when water molecules are broken apart by ultraviolet light. It's a completely natural process observed in countless comets. The mystery signal wasn't mysterious. It was water doing what water does near the sun. But here's where the controversy gets complicated. Even though the artificial hypothesis lacks supporting evidence, the natural explanations aren't satisfying either. We still don't have a complete, universally accepted model for why 3I Atlas survived perihelion. We still don't fully understand its composition or structure. The mainstream position is basically this: we don't know exactly what's going on, but we're confident it's natural. That's a reasonable scientific stance, but it leaves room for speculation to flourish. Stepping back from the artificial debate, there are deeper implications worth considering. We've now observed 3 confirmed interstellar objects: 1 I/Oumuamua, 2 I/Borisov, and 3I Atlas. Each one has been different. 1 I/Oumuamua was elongated, had no visible coma, accelerated in ways suggesting outgassing, but without detected gases. 2 I/Borisov looked like a fairly normal comet, similar to many in our solar system. 3I Atlas combines extreme compositional anomalies with structural resilience and weird polarimetry. 3 data points don't make a statistical sample, but they hint at something important. Interstellar objects might be far more diverse than we anticipated. If every visitor looks different, that challenges our ability to make generalizations. It also raises questions about how representative any single object is of its birth environment. Can we really infer properties of another star system from one comet that's been traveling through space for unknowable eons? The cosmic ray processing hypothesis, if correct, adds another layer of complexity. If every interstellar object gets its surface chemistry and structure modified during travel, then what we observe isn't pristine formation material. It's weathered, processed, altered. Like trying to deduce the composition of bedrock by studying sand on a beach. You can learn something, but you're seeing the product of transformation, not the original state. This has practical implications for future missions. Space agencies are considering proposals to intercept and study interstellar objects up close, maybe even return samples. But if these objects have hardened crusts from cosmic ray bombardment, a sample return mission might need to drill or penetrate deeper than initially planned. Mission designs might need to account for structures more resilient than typical comets. The engineering requirements change. There are also implications for how we communicate science to the public. 3I Atlas demonstrates the tension between careful scientific uncertainty and the public's desire for clear answers. Scientists say, we don't know yet. We need more data. Several hypotheses remain plausible. That's intellectually honest, but unsatisfying. Media and public discourse prefer definitive statements. Is it alien or not? Will it hit us or not? What's the truth? This communication gap can erode trust. When headlines promise cosmic mysteries and scientists respond with hedged statements full of caveats, some people conclude scientists are hiding something. When scientists firmly state that natural explanations are more likely but can't yet prove which natural explanation is correct, it can sound like weakness rather than intellectual rigor. The broader astronomical community is grappling with how to handle this. Some argue for more aggressive public engagement, meeting speculation with clear explanations of why certain ideas are unlikely. Others worry that giving too much attention to fringe hypotheses legitimizes them. There's no easy answer. Science advances through data and analysis, but it exists within human culture, subject to interpretation, emotion, and narrative. 3I Atlas sits at the intersection of all these tensions. It's a real object with real anomalies demanding explanation. It's also a symbol, a canvas onto which we project our hopes, fears, and questions about our place in the cosmos. The scientific process will eventually deliver answers, or at least better models. But in the meantime, the object forces us to confront how we handle uncertainty, and what we do when the universe gives us something genuinely unexpected. The implications ripple outward. If our models of comet behavior need significant revision based on 3I Atlas, that affects our understanding of comet formation in our own solar system. It affects models of planetary system evolution. It affects estimates of how many interstellar objects are passing through at any given time and what fraction we're detecting. Every assumption downstream from basic comet physics needs to be revisited. For planetary defense, the effort to detect and potentially deflect dangerous asteroids, this matters too. If small bodies can be more structurally resilient than we thought, deflection strategies might need adjustment. A kinetic impactor designed to fragment a rubble pile might behave differently against a body with a hardened crust or strong internal structure. 3I Atlas is teaching us that the universe is more varied than our categories suggest. We built our understanding of comets from centuries of observation, but those were all family members, objects from our solar system. Now, the neighbors are stopping by, and they don't always fit the molds we've prepared. That's uncomfortable. It's also exactly what science is supposed to be about, letting reality, not expectation, guide our understanding. While 3I Atlas captures headlines with its peculiarities, it may be pointing towards something larger, a shift in how we understand the long-term evolution of small bodies, especially those wandering through interstellar space. The cosmic ray processing hypothesis isn't just an explanation for one weird comet. It's potentially a new paradigm for thinking about what happens to objects during the vast, lonely stretches between stars. Let's establish what we mean by cosmic ray processing. Galactic cosmic rays are high-energy particles, predominantly protons, that originate from supernova remnants, active galactic nuclei, and other violent astrophysical events. They permeate the galaxy, traveling at significant fractions of light speed. When these particles impact solid matter, they don't just bounce off. They penetrate, colliding with atoms and molecules, breaking chemical bonds, depositing energy, triggering cascades of secondary reactions. For an object traveling through interstellar space for millions of years, this bombardment is relentless. Surfaces exposed to cosmic rays undergo radiolysis, radiation-induced chemical decomposition. Simple ices can be transformed into more complex molecules. Carbon monoxide can oxidize to carbon dioxide. Methane can be broken down and reassembled into larger organic molecules. Crystalline structures can become amorphous. Virgin material becomes processed material. But it's not just chemistry. The physical structure changes too. Radiation damage can create defects in crystalline lattices, making materials more brittle or paradoxically more cohesive as broken bonds reform in new configurations. Organic materials can polymerize, creating tougher, more refractory substances. Over sufficient time, the outer layers of an icy body could develop a hardened crust fundamentally different from the interior. This isn't pure speculation. We've seen hints of similar processes in our own solar system. Kuiper belt objects and other distant bodies show spectroscopic signatures suggesting radiation-processed surfaces. Laboratory experiments where scientists bombard ice samples with high-energy particles produce chemical changes consistent with what we observe on some outer solar system bodies. But these objects have spent their lives in the relatively mild radiation environment of our solar system, protected by the heliosphere, the bubble of solar wind that partially shields us from galactic cosmic rays. 3I Atlas spent its journey naked to the full fury of interstellar radiation. No heliosphere, no stellar wind to deflect or slow cosmic rays. Just raw exposure for however long it wandered. If cosmic ray processing creates measurable effects in our solar system over 4.6 billion years, imagine what it could do to an object traversing the galaxy for potentially much longer, with much higher radiation flux. The implications cascade outward. If this paradigm is correct, then every interstellar object we observe is telling us about two different stories, simultaneously. First, the formation story, what the object was like when it condensed in its birth system. Second, the journey story, how cosmic ray processing altered it during transit. Disentangling these two narratives becomes crucial if we want to use interstellar visitors as probes of other planetary systems. Consider what this means for future space missions. Several proposals exist for intercepting and studying interstellar objects up close. Some envision fast flyby missions that would capture images and spectra. Others imagine more ambitious rendezvous missions that could orbit an interstellar visitor, studying it in detail. The most ambitious proposals talk about sample return, landing on the object, collecting material, and bringing it back to Earth for laboratory analysis. But if cosmic ray processing creates a hardened crust, missions need to account for that. A surface scoop might only collect processed material, missing the pristine interior that actually tells us about formation conditions. Drilling becomes necessary. The engineering requirements shift. Power requirements increase. Mission designs that assumed comet-like fragility might need revision to handle unexpected structural strength. The paradigm also affects how we interpret compositional data. When 3I Atlas shows extreme carbon dioxide dominance, is that telling us about where it formed? Maybe near a carbon dioxide ice line in an unusual protoplanetary disk? Or is it telling us that cosmic rays converted surface carbon monoxide to carbon dioxide over eons? Without understanding the processing, we risk misinterpreting the formation story. This uncertainty compounds for population studies. Astronomers want to estimate how many interstellar objects pass through our solar system each year. Those estimates depend on detection probability, which depends on assumed brightness, size distribution, activity levels. If cosmic ray processing makes interstellar objects behave differently from our solar system comets, maybe they're less active because hardened crusts suppress outgassing, or maybe they're more active because gas builds up under the crust and vents explosively, then our detection models need adjustment. Future surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will dramatically increase our ability to detect faint, fast-moving objects. We're going to find more interstellar visitors. Many more. But interpreting what we find requires understanding what we're looking at. Are we seeing formation signatures or processing signatures? The cosmic ray processing paradigm forces us to think carefully about that distinction. There's also a philosophical dimension here. One reason we're excited about interstellar objects is that they're samples from other stellar systems, free, delivered to our doorstep by cosmic chance. We don't need to travel light years to study extrasolar material. We just need to wait for it to come to us. But if the journey fundamentally alters the material, then what we're studying is as much the journey as the origin. The interstellar medium becomes part of the story, not just the background against which the story unfolds. This actually makes the science richer, not poorer. We learn about both planetary formation elsewhere, and about the conditions in the space between stars. We learn about chemistry and physics at timescales and radiation doses we can't easily replicate in laboratories. We learn about material evolution in ways relevant to understanding the life cycle of matter in the galaxy. Applying this paradigm specifically to 3I Atlas helps explain multiple features simultaneously. The carbon dioxide dominance, cosmic ray oxidation of carbon monoxide. The structural integrity, a radiation-hardened crust holding things together. The unusual polarimetry, surface grains modified by radiation damage showing scattering properties we haven't cataloged. The survival at perihelion, that protective processed shell resisting thermal and tidal stress. Not every detail fits perfectly yet. We don't know the crust thickness. We don't know whether it's uniform or patchy. We don't know the exact mechanical properties or how they compare to laboratory irradiated samples. But the framework provides a coherent narrative that accounts for observations better than assuming 3I Atlas is just a normal comet that happens to be from elsewhere. The paradigm suggests predictions we can test. If cosmic ray processing is common, we'd expect other interstellar objects to show similar signatures. Future visitors might also display carbon dioxide-rich compositions, unusual polarimetry, structural resilience. We'd expect a correlation between estimated age, inferred from trajectory and stellar encounter history, and degree of processing. Older objects should show stronger signatures. We can also test this in our own solar system. Objects from the Oort cloud, our sun's distant reservoir of comets, spend most of their time far from the sun, where cosmic ray exposure is higher. When they fall inward and become active, do they show compositional or structural differences from short-period comets that stay closer to the sun? Subtle differences might already exist in the data, waiting for someone to look with this paradigm in mind. 3I Atlas might be remembered not just as a weird individual object, but as the case study that forced a paradigm shift. The comet that made us realize interstellar objects aren't just exotic versions of our comets. They're processed, altered, evolved by their journey through conditions we're only beginning to understand. Every wanderer carries two histories, and reading both requires new tools, new models, and new ways of thinking about the deep time between stars. 3I Atlas doesn't exist in isolation. While this strange visitor captures our attention, it's part of a broader moment in astronomy, where multiple revolutions are converging. The way we study space, the tools we use, and the questions we ask are all transforming simultaneously. To understand the significance of 3I Atlas, we need to see it against the backdrop of these parallel developments. Start with artificial intelligence in astronomy. Machine learning algorithms are revolutionizing how we find and classify celestial objects. Traditional sky surveys generated data faster than humans could analyze it. Images piled up. Transient events, things that change brightness or position, went unnoticed because there was simply too much data for human eyes to scan. Now, neural networks trained on millions of examples can identify unusual objects in real time. This matters for interstellar visitors specifically. These objects move fast and appear faint. They're easy to miss if you're not looking at the right place at the right time. But AI systems can flag anything with a hyperbolic trajectory or unusual motion, alerting astronomers to potential interstellar objects within hours of detection. Earlier detection means more time to mobilize telescopes, plan observations, and gather data before the visitor fades into the distance. If 3I Atlas had been discovered earlier in its approach, we might have captured more pre-perihelion data. We might have watched its activity ramp up in higher detail. We might have better constraints on its size and composition. The next interstellar visitor will benefit from these improved detection systems. We're building an early warning network for cosmic strangers. AI also helps with interpretation. Researchers are training models to classify spectra, identify composition signatures, and even suggest formation scenarios based on observed properties. When confronted with something as anomalous as 3I Atlas, AI systems can search through archives of comet and asteroid data looking for partial matches or analogs. Maybe no single object matches, but combining features from several different classes of objects might point toward explanations human intuition would miss. But AI is a tool, not an oracle. It finds patterns in existing data. It can't imagine entirely new physics or propose hypotheses that require stepping outside the training set. That still requires human creativity, intuition, and willingness to consider uncomfortable possibilities. The future of astronomy will be a collaboration, AI handling the data deluge, humans handling the conceptual leaps. Meanwhile, planetary defense has matured from theoretical concern to active field with real infrastructure. Organizations like NASA's Planetary Defense Coordination Office track near-Earth objects, catalog risks, and develop mitigation strategies. Recent years have seen successful demonstrations like the DART mission, which deliberately impacted an asteroid to test deflection techniques. But 3I Atlas and other interstellar visitors add a wrinkle to planetary defense. These objects aren't in predictable orbits. They appear with little warning, moving at high velocities. If an interstellar object were on a collision course with Earth, we'd have less time to respond than for a typical near-Earth asteroid. And as 3I Atlas demonstrates, we don't fully understand how these objects behave structurally. Deflection strategies depend on knowing what you're hitting. Kinetic impactors work differently on solid monoliths versus rubble piles. Nuclear deflection, detonating a device near an object to vaporize surface material and create thrust, depends on composition and structural integrity. If interstellar objects have radiation-hardened crusts, our models for how they'd respond to intervention might need revision. This isn't immediate cause for alarm. The probability of an interstellar object hitting Earth is vanishingly small. But as we find more of these visitors and realize they're more diverse than expected, planetary defense planners are taking notice. The universe might throw us a curveball someday, and preparation means understanding the full range of what's out there. Let's pull back and summarize the journey we've taken. We started with a simple observation. 3I Atlas didn't break up when it should have. That led us into the details of what telescopes actually saw. bizarre composition, unprecedented polarimetry, structural resilience, unusual activity. We explored why survival is paradoxical given our understanding of comet physics. We examined hypotheses ranging from cosmic ray processing to exotic compositions to speculative artificial origins. We've seen how 3i Atlas generates controversy, revealing tensions about how science handles uncertainty and communicates with the public. We've explored the cosmic ray processing paradigm and how it might reshape our understanding of interstellar objects and small body evolution. And we've placed this discovery within the broader context of AI-driven astronomy and planetary defense concerns. So what are the key takeaways? 3i Atlas survived conditions that should have destroyed it. That's the central anomaly. Its composition, dominated by carbon dioxide, suggests either an unusual formation environment or significant processing during its journey. The polarimetric signature is genuinely unprecedented, indicating surface or coma properties unlike any cataloged object. Multiple observations from independent facilities confirm this isn't instrumental error or misinterpretation. It's real, and it demands explanation. Several hypotheses exist to explain these features. Cosmic ray processing, creating a protective hardened shell, is currently the leading natural explanation among researchers seriously engaging with the data. Exotic internal composition or structure, maybe metal-rich, maybe layered in unusual ways, remains plausible but lacks direct evidence. Artificial origin, while popular in some circles, has no supporting evidence beyond anomalies that can be explained naturally, even if we don't yet know. Which natural explanation is correct? The implications extend far beyond one object. For interstellar object science, 3i Atlas suggests, we've been underestimating diversity and overestimating our ability to interpret what we see. For comet and small body physics, it hints that our models derived from solar system objects might not be universally applicable. For mission planning, it warns that interstellar visitors might be structurally tougher than expected, requiring different engineering approaches. And for public understanding of science, 3i Atlas demonstrates both the excitement and the frustration of working at the edge of knowledge. We don't have all the answers yet. We might not have them for years. More data will arrive as observations continue. Models will be refined. New hypotheses will emerge. Some current ideas will be ruled out. Others will gain support. This is how science actually works. Not as a steady march toward truth, with each day bringing clarity, but as a messy, uncertain process where every answer raises new questions and every observation opens new mysteries. 3i Atlas is a perfect case study because it's happening now, in real time, with researchers publicly grappling with what they're seeing. We live in an extraordinary moment for astronomy. Our telescopes can see farther and clearer than ever before. Our computational tools can process data at scales that would have been impossible a generation ago. Our theoretical frameworks have expanded to encompass exoplanets, gravitational waves, dark matter, and now interstellar visitors. But with each expansion comes humility. The universe is bigger, stranger, and more inventive than we imagined. 3i Atlas is a messenger from that larger, stranger universe. It arrived from beyond our solar system, carrying questions we didn't know to ask. It survived when our models said it shouldn't. It behaves in ways that challenge our categories. And perhaps most importantly, it reminds us that despite all our knowledge and sophisticated tools, the cosmos still has the capacity to surprise us. If 3i Atlas could survive what physics said should destroy it, what else is out there that contradicts our expectations? How many other visitors are passing through our solar system right now? Too faint or too fast for us to detect? What will we find when our surveys improve and we start cataloging dozens or hundreds of interstellar objects? Will they all be as weird as 3i Atlas, or is this one an exception? These questions don't have answers yet. They're invitations to keep looking, keep questioning, keep pushing against the boundaries of the known. 3i Atlas won't be the last interstellar visitor to confound our models. It might not even be the weirdest, but it's the one we're grappling with now, the puzzle currently demanding our attention and imagination. As the object recedes, growing fainter each day, the window for observations slowly closes. Some Questions about 3i Atlas may never be fully answered. We'll move on to the next discovery, the next anomaly, the next cosmic mystery. But the lessons remain. Our models are incomplete. Our understanding is provisional. And the universe, vast and ancient and indifferent to our theories, will keep sending us surprises. That's not a weakness of science. That's the entire point. We build the best models we can with available data, knowing they'll eventually be superseded by better models incorporating new observations. 3i Atlas is one of those observations that forces revision. What emerges on the other side, new paradigms, refined physics, expanded possibilities, will be stronger precisely because it had to account for something that didn't fit. So here's the final thought to carry forward. When something survives, what should destroy it? When something behaves in ways that contradict expectation? When the universe hands you an anomaly, pay attention. Because anomalies are where the frontier lives. They're where our knowledge ends and the unknown begins. 3i Atlas is standing on that frontier right now, silhouetted against the darkness between stars, asking us a simple question. Do we understand the universe as well as we think we do? The answer, increasingly clear, is no. But we're learning. And every strange visitor, every unexplained observation, every challenge to our models brings us one step closer to understanding not just what's out there, but the limits of what we thought was possible. The universe just got stranger. And that's exactly what makes it worth watching.